Hi everybody, welcome to another SUPA lecture. Today we're going to be doing a bunch of physics actually, so those of you that have physics, this will be a review. And we're going to start talking about light. And light is what's called electromagnetic radiation. So it's got waves. So this is electromagnetic radiation. Now, light is one type of electromagnetic radiation. There's lots of other types. So we'll refer back to this often. So visible light, okay, are different colors. There's other types of electromagnetic radiation. Ultraviolet light is electromagnetic radiation. X-rays, gamma rays, these are electromagnetic radiation. Infrared, radio waves. Now the radio waves we're talking about here are the waves that go from the station to the radio itself, not from the radio to your ears. Okay, so these are all different types of electromagnetic radiation. Again, we have to define some things here. So let's talk about wavelength. And the wavelength is the distance between two crests or two troughs. Okay, so we're talking about this distance from here to here. Okay, so that would be on crests, and these are the troughs over here. So you can measure it either way. That's the wavelength. Okay, and we use the lambda sign. And wavelength is expressed in units of length. It's usually in nanometers. Or angstroms. Oops, sorry. That's an A with a degree sign up top. Angstroms. You should be able to do some conversions between all these things too. So I'm going to give you those factors here. So 1 nanometer is equal to 10 to the minus 9th meters. Or you could say 1 meter is equal to 10 to the 9th nanometers. 1 angstrom is equal to 10 to the minus 10th meters. Okay, so you'll need these conversions. Okay, so I would definitely learn those. Okay, so this is our wavelength. Next term we have to quickly talk about is called frequency. And that's the number of wave cycles that pass a given point in a second. Okay, so what we're doing is we're timing a wave cycle. Now a wave cycle, okay, it would be from here to here. How many times we have that go through a specific point in a second, and you just time it. So you would just count how many of these, this is the wave cycle, goes through a point, and it can be any point. I could pick this one and say, okay, how many cycles will I get in 1 second? Now, usually it's expressed The symbol we use is a nu. It's a nu. This is kind of like a V. And it's expressed in inverse seconds. So it's per second, or seconds to the -1, or hertz, which is Hz. All right, so our wavelength is inversely proportional to frequency. So mathematically, wavelength is inversely proportional to frequency. That's a new sign, sorry. Now what does that mean? Well, what that really tells us is the higher the frequency, the shorter the wavelength. Okay, so if we go back to this little piece, this diagram right here, okay, so these have very long wavelengths over here. So the frequencies, okay, they're going to be less frequent. The frequency is going to be less. Over here we got really short wavelengths. Okay, and we're going to have lots of waves passing a specific point, okay, per second. Okay, so if we have short wavelengths, we have high frequency. If we have long wavelengths, we're going to have longer wavelengths, we're going to have lower frequencies. Okay, so it's that inverse relationship between frequency and wavelength. Now there's a formula that you do need to know. Wavelength times frequency equals c. And c is the speed of light in a vacuum. And the speed of light in a vacuum is 3.00 times 10 to the 8th meters per second. And you should definitely know this number, okay, because we'll be using it. Now we could rearrange this. Wavelength equals speed of light over frequency. Frequency equals speed of light over wavelength. Okay, so that's just rearranging the equations. So we'll be using these equations to calculate wavelength and frequency. Let's talk about amplitude. So our amplitude refers to intensity of the radiation. Higher the amplitude, higher the intensity. Well, what does that look like what does it look like on the wave itself? Okay, well, let's draw it. I'm going to draw two different waves. Okay, so we'll have one wave here, and we'll have one wave here. Okay. Now, I tried to do the wavelength about the same, and I think I came pretty close. Okay, well, the difference is this. This right here, from the top of the crest to this line, that is the amplitude. Okay, that's the amplitude. So over here, this would be my amplitude. Okay, this one's much more intense electromagnetic radiation than this one. So the wavelength doesn't change, the frequency is not changing, it's just, okay, the amplitude's changing, which is your intensity of the light. We don't do much, we don't do a whole lot with intensity, right? But most of the stuff that we're going to be dealing with is over here with frequency and wavelength. So let's try a couple problems before I give you another equation. So let's try this. The sodium vapor lamps on a highway have a wavelength of 587.8 nanometers. Calculate the frequency of the light wave. Well, we need to eventually get to use frequency equals C over wavelength. Okay, the problem is speed of light is in meters per second, and this is in nanometers. So the very first thing I want to do is I want to convert this to meters. Okay, so I got to convert my distance to meters. And to do that, we know that the wavelength is equal to 587.8 nanometers. Okay, I can use dimensional analysis. Okay, for every 1 meter, we have 10 to the 9th nanometers. Okay, so this turns out to be 587.8 times 10 to the minus 9th meters. Right, so I need to use that one for my wavelength. So now I can just substitute in my wavelength, or my frequency, equals the speed of light, 3.0 times 10 to the 8th meters per second, divided by 587.8 times 10 to the minus 9th meters, and I end up with let's use 3.00. With sig figs, we end up with 5.10 times 10 to the 14th inverse seconds. Okay. That would be my frequency. I could also say 5.10 times 10 to the 14th waves per second or hertz. Okay. Either one of them is acceptable. So this would be my frequency. Let's try another one. Light has a frequency of 7.14 times 10 to the 14th hertz. Calculate the wavelength in nanometers. Okay, so here's my frequency. Okay, so the light is 7.14 times 10 to the 14th hertz, or waves per second. So our frequency equals speed of light over wavelength. Okay, or we can rewrite this and say wavelength equals speed of light over frequency. And we can substitute. And we get 3.00 times 10 to the 8th meters per second divided by 7.14 times 10 to the positive 14th hertz. So I end up with 4.20 times 10 to the minus 7th meters. Okay. So this number is in meters. It asked for it in nanometers, so I got to convert it. So I take 4.20 times 10 to the minus 7th meters. For every 1 nanometer, I have 10 to the 9th meters. So that gives me 420 nanometers. Okay, and all 3 of them are significant, so you either need a decimal point or you got to put a bar over that 0. So I got 420 nanometers, and that would be my answer. These are pretty simple calculations. I don't think you'll have any trouble with those. So now we want to know, now we have to take the next step. Now that we can calculate wavelength and frequency of light, we're going to take the next step. So if we look at this electromagnetic spectrum, it's arranged in, well, this one's arranged in decreasing wavelength. Okay, and okay, so my high wavelengths, my short wavelengths are down here. Okay, quick frequencies. In class, we're going to be dealing mostly with visible light. Okay, so we're going to be dealing with, and this is, if you remember, Roy G. Booth, right? So we got our reds, oranges, yellows, greens, blues, and violets down here. So we'll be using mostly this visible section of light. Okay, so let's write a couple things. So let's write the electromagnetic spectrum. And it's usually arranged in order of, increasing wavelength. So it usually starts around the range is considered to be from 10 to the minus 15th meters, and it goes up to 10 to the 9th meters. These are what's called, these are really long wavelengths, and these are ultra low frequency waves. And if we're in this wavelength, we're talking about gamma rays. Now, electromagnetic radiation has a duality. It has a duality, which means sometimes it acts like it's waves. But sometimes it acts like it is particles. So you may have heard of the duality of light. Okay, so light sometimes behaves like it's a wave, but sometimes it behaves like it's particles. All electromagnetic radiation has that duality. So our electromagnetic radiation are made up of photons. So these are individual packets of energy. Okay, so if we go back to our wave, so sometimes the radiation acts like it's in waves. But these waves are made up of tiny particles. And they're moving in this direction, they're moving like a wave, but that tiny particle is called a photon. Okay, it's a packet of energy. And we can actually calculate the energy associated with a photon of light. So the energy of a photon is directly proportional to frequency. So as frequency increases, the energy of that photon also increases. So if we have long wavelengths, okay, or very low frequency, it's going to have very low energy. But if the frequency is high, okay, that means we got lots and lots of waves happening. All right, that means those photons have a lot of energy. And we can actually derive a formula, sort of. So the energy of that photon is equal to something called H times our frequency. H is what's called Planck's constant. And that's another number you need to memorize. 6.626 times 10 to the negative 34th joule dot seconds. Okay, this is Planck's constant. So the energy of that photon is equal to Planck's constant times frequency. Now, do we have a formula for frequency? Well, we know frequency equals the speed of light over wavelength. So we can actually substitute into the equation, and energy equals Planck's constant times the speed of light over wavelength. Okay. So you really have a bunch of different equations here. Okay, so this is the energy of the photon, Planck's constant, and we're dealing with frequency. Here it is with wavelength. Okay, and we've already used this equation. So now, what is this equation telling me? Well, if we have the higher the frequency, higher the energy. If we look at wavelength, though, smaller the wavelength, the higher the energy. Now, like I said, we're going to deal with visible light. So the visible region of the spectrum of the electromagnetic spectrum is broken down into color. And you can just think about the rainbow, because that's what this is. Okay, so Roy, G, both. So now, every single color has its own wavelength. So let's look over here. So so there's lots and lots of reds, okay? So if I go from 700 to 701 nanometers, okay, that's a different color of red, okay? What are these by? 20, 40, 60, 80. So 720 is definitely much darker red than 700. Right? Same thing over here, just a little change from, if we're here at 580 nanometers to 600, 600 were in those yellows, 580 were in green. So every single wavelength has its own very specific color of light. Now, the visible spectrum, which is what we call it, okay, our wavelength generally goes from about 400 nanometers up to about 750 nanometers. And these would be our violets, and these would be our reds. Now, which one has more energy, the violets or the reds? Well, remember, okay, if we have small wavelengths, we have high energy, so violets have more energy. Okay, our longer wavelengths has less energy, so our red has less energy. Now, what if I have a single wavelength of radiation? Let's say that I have a wavelength of radiation that is exactly 600 nanometers. It would be a yellow color. If you only have one single wavelength, it's got a special name. A single wavelength of radiation is called monochromatic light. Mono means one. Okay. So we got one wavelength of light. Okay, now lasers generally are monochromatic. Okay, so your lasers, if you see a laser, okay, that's one thing, it's producing one wavelength, and that would be monochromatic. All right, let's try some calculations. Calculate the energy in joules for red light having a wavelength of 629.7 nanometers. Well, the first thing that I see is that we can't be in nanometers. We have to be in meters. So the very first thing we're going to do is we're going to convert this wavelength into meters. Okay, so our wavelength is 629.7 nanometers. 10 to the 9th nanometers is 1 meter. So we end up with 6.297 times 10 to the minus 7th meters. So now it's in the correct unit that I can actually substitute in. And I want to calculate the energy of that wavelength. So I can say the energy of that wavelength is equal to Planck's constant times the speed of light divided by wavelength. Well, we know what Planck's constant is now. And I'm going to do it this way. 6.626 times 10 to the negative 34 joule seconds times 3.00 times 10 to the 8th meters per second divided by 6.297 times 10 to the minus 7th meters. That's my wavelength.